stern. Well, my stern appearance has something to do with slight stomach problems, but I hope they will not interfere with my lecturing. So this is a talk about large quantum systems. The mathematical results I'm going to talk about are joint results with Tsai and Yao. And the questions, I mean, since Misha emphasized that one should try to ask good questions, the questions were originally asked by Tom Spencer and myself rather many years ago. All right, so here is a brief list of contents which you can look at. Of course, I thank the organizers for the generosity to invite me to attend this meeting. So, I think I should not talk about visions. My reputation is already a little hampered, so I will not do visions. And I'm afraid the mathematics will not be terribly deep, but I believe that Jean Bourgain will talk about deep results in a similar direction. So I'm going to cover more the physics, why this is interesting for a physicist. So, in fact, the main question I'm going to address is the following one. In which limiting regimes does quantum theory reduce to classical Hamiltonian dynamics? I mean, when you look around, this world looks pretty classical, so we would like to understand how classical behavior emerges from quantum theory. It is sort of the inverse to the problems that the mathematicians have been fascinated with lately in the work of Kontsevich, for example, namely to understand quantization. I will try to understand how to dequantize. Now, in fact, we want to do a little more. We do not just want to understand how classical dynamics emerges from quantum theory. We would like to understand how the Newtonian dynamics of point particles might emerge from quantum theory. And in fact, we might want to understand how friction appears in the sense of Aristotelian physics. I think these are basic questions in trying to understand quantum theory. In fact, we are going to celebrate 100 years of quantum mechanics or quantum theory in just a few months from now, and I guess we have to admit that after 100 years we still don't quite know what it all means. So this is a modest attempt to try to offer some ideas how the classical world comes back. So I prepared a few introductory remarks, but I don't want to spend much time on them. So the problem will be how to go from large systems of weakly interacting non-relativistic quantum mechanical particles back to classical field theory, and from there to Newtonian mechanics. All right, that's the issue of these lectures. Of course, this is just one among many interesting problems. One of the most challenging circle of problems concerns highly correlated or strongly coupled large quantum systems. In fact, I will do the easier part. I will look at large quantum systems, but with weak coupling and without any particularly complicated quantum mechanical correlations. But in the end, what we are mostly interested in is to understand highly correlated large quantum systems. For example, low energy quantum chromodynamics which is very poorly understood, or the phase transitions that appear in many body theory, such as Bose-Einstein condensation or superconductivity, or the metal insulator transitions that have become quite fashionable in recent years, or things like marginal Fermi liquids, the fractional quantum Hall effect, or stellar physics. The mathematical methods that people use to address such problems are renormalization group methods, conformal field theory techniques, in short, hard analysis and computing. So this talk will be really about analysis. Of course, there are more speculative problems that we would like to understand and make progress with, but I'm not going to talk about that. Maybe the next talk will be more in this direction, namely the unification of quantum theory with the theory of gravitation. That's really sort of the ultimate frontier at the moment, and it is perhaps a little astonishing that, as far as I know, nobody really will talk about this at this meeting, as far as I know. All right, so let's now start on the subject of this lecture proper. So let's start with a little introduction about quantum mechanics. The state space of a quantum system is a separable Hilbert space. A pure state is a unit ray in this Hilbert space, or a mixed state is a Hilbert-Schmidt operator with the property that rays kappa star kappa equals 1. The time evolution of such a state is described by Schrödinger's equation, IH bar dt psi equals H psi, where H is the Hamilton operator. It is supposed to be a self-adjoint operator. The physical, this is totally abstract. There is no meaning to this. So in order to come up with meaning, we have to choose a certain algebra of operators that encodes the physics of the system under discussion. And then the time evolution in the Heisenberg picture of the observables in this algebra A, of course, is given by, as usual, A of t is e to the I h t over h bar, A e to the minus I h t over h bar. All right. So let's make some examples. The examples that are particularly relevant for this lecture is the following one. I consider n spinless, non-relativistic, identical particles moving in physical space, which for the purpose of this lecture is simply Euclidean 3 space. They feel the influence of an external potential W, and they may have two-body interactions described by a potential phi. The algebra that encodes the physical situation is then, for example, an algebra of functions that depends on the positions of these m particles. The function A is smooth and totally symmetric under permutations of the arguments. The Hilbert space is a space of square integrable wave functions. And now comes a very important concept. Since the particles are identical, we have to specify how the state vectors transform under permutations of the particles. In other words, we have to specify a certain representation sigma of the permutation group of n elements. If this representation is the trivial representation, we talk of Bose-Einstein statistics. If it is the alternating representation, it is Fermi-Dirac statistics. There are, of course, in principle, higher dimensional representations coming up. They are called parastatistics, and there are theorems which say that parastatistics can always be converted into ordinary statistics at the price of introducing internal degrees of freedom. This played a big role in the history of particle physics, of the quark model, for example. The Hamiltonian for this n-particle system, I'm looking at non-relativistic particles, so it is of the form a kinetic energy operator, which is the first term on the right-hand side of this Hamiltonian. This one, then the external potential, and then the two-body interactions. I have set the mass of the particle to 1. It will be advantageous for my purposes to make use of the formalism of second quantization. For example, it could happen that this m-particle system is really connected to a reservoir with which it can exchange particles. Then n, capital N, the number of particles may fluctuate, and then it is advantageous to take as a state space the Fock space, that is the direct sum of all the m-particle spaces. The zero-particle space is simply the complex numbers. Vectors in the Fock space are sequences of m-particle wave functions where n is anything between 0 and infinity. Here is the scalar product on Fock space. Then if we want to destroy or eliminate the particle, we do that by applying an annihilation operator to the state vector psi. And I have defined how annihilation operators act on vectors in Fock space in the next line. This is all completely standard material. I hope that people in this room are more or less familiar with these things, this sort of elementary quantum mechanics of second quantization. The creation of a particle is then simply described by the adjoint operator, the adjoint of the annihilation operator. The Hamiltonian of the system is the direct sum of all the m-particle Hamiltonians, and of course, when there is no particle in the universe, the energy is 0. So what are typical problems that we would like to understand about such large systems of non-relativistic quantum mechanical particles? The most basic problem that you can think of is the thermodynamic stability. You would like to understand whether the n-particle Hamiltonian is bounded from below by a constant times the number of particles, so that the energy per particle remains finite independently of how many particles there are in the system. Stability usually can only be proven if some of the particles are satisfy Fermi-Dirac statistics. For Bose-Einstein statistics, you get the higher power of n, and usually large systems of bosons are not stable in the sense of thermodynamics. Then, of course, a related problem is the question of whether the thermodynamic limit exists. So you would confine the system to a box, lambda, keep the density rho, which is the mean number of particles divided by the volume of the box, fixed, and then let the volume of the box tend to infinity. Another problem that is interesting, that has become quite fashionable in recent times, is the question of Bose-Einstein condensation. Is it possible to prove for systems of many bosons that in the thermodynamic limit gauge invariance is broken, in the sense that if you take a state of the infinite system and you calculate the expectation value of an annihilation operator, you would like to show that this is non-zero, that would signal Bose-Einstein condensation. If you look instead of systems of bosons at systems of fermions, you might want to understand things like Cooper pairing and superconductivity, marginal Fermi liquids, Hall liquids, and the like. But this is not what I'm going to talk about. This is just a little survey of good questions that we should worry about. What I shall talk about is the problem of the classical limits. So let's consider an m-particle system. Psi n is a state of this system. A is an observable in the algebra A. And TA is a time scale which tells me how long I have to wait till the expectation value of this observable A in the state psi n changes appreciably. Of course, the time evolution of the state is described by the Schrödinger equation. Now we can calculate the action of a trajectory of states by calculating the expectation value of the Hamiltonian and then integrating over time from 0 to this time scale t of a. A necessary condition for classical behavior to emerge in quantum theory is that this action is much, much larger than Planck's quantum of action. The classical limit is a limit of large actions. If the system is stable, we may hope to show stable in the thermodynamic sense that I introduced a minute ago. Then we may hope that classical behavior will emerge when the number of particles is very large, because a typical action is expected to be proportional to the number of particles. So we would expect that the classical limit will appear for very many particles. A comment on the role of h bar. H bar is 1. I can always choose my units such that h bar has the value 1. It is a bad habit of mathematicians, and which has also corrupted some of the physicists, that they vary h bar and let it tend to 0. This is really not the right idea about the classical limit. All right, so now I'm going to consider an example for which these general ideas about classical limits can be made reasonably precise. And this is a system of many, many bosons with very weak two-body interactions. So I consider a system of n bosons, for example, neutral atoms or molecules interacting via van der Waals attraction and also gravitational attraction. In fact, I think that's not uninteresting to include gravitational attraction. Yeah, but you see, if I want to, for example, look at these little bosonic stars which have about the size of a mountain, then of course the gravitational interactions are perfectly relevant. All right, so the statistics is described by the trivial representation of the permutation group, and then we have the Fock space, the m-particle Hamiltonians, etc., all as introduced before. I introduce a coupling constant. I say that my two-body potential is a parameter kappa times phi c, and kappa will be very small. This is a good thing when you look at, say, van der Waals forces between atoms, because in comparison to typical kinetic energies, the potential energies are small. So the potential phi c should be at least in L3 halves, and for various purposes, we need some bounds on first and second derivatives of phi c.
So phi is the potential?
Phi is the name for the two-body potential. Now, I would like to vary the strength of the two-body potential, so I write phi as kappa times phi c. Phi c is fixed, say 1 over r, and kappa will be varied. All right. All right, so phi c should be bounded, say, by the two-particle Hamiltonian in the sense of Kato and Rellich. So let's look at an example. For example, phi c of x could be x to the minus 6. This is van der Waals. And plus g times x inverse, that would be the Newtonian gravitational potential. This is the behavior for x large. I may permit myself to introduce a short distance regularization. So in other words, I will cut off the singularities at x equals 0. So I introduced the creation and the annihilation operators just a few minutes ago. Since I now look at Bose-Einstein statistics, these annihilation and creation operators can be verified to satisfy the canonical commutation relations. A of f commutes with A of g, and A star of f commutes with A star of g. And the commutator of AF with A star of g is given by the scalar product of f with g times the identity.
A of f is a vector, yeah? It's not a
No, A is an operator. It's the annihilation operator.
like the f,
F is a test function. A is an operator-valued distribution, so if you smear it out with a test function, it becomes an unbounded but rather pleasant operator about which much is known. Should I recall the definition of the annihilation operator, or is it okay?
Because you imply that relates to f, yeah? This is
All right, well, don't get you see, here is the definition once more. It just eliminates a particle in one single particle in the state f from an m plus 1 particle state. All right, so we can rewrite our Hamiltonian in second quantized notation. I mean, look, either you have seen these formulas and done a few calculations with them, then they look obvious to you. If you have never seen it before, all this may look a little strange, but it is mathematics. I mean, this is it's not difficult to make all this precise. Well, since we are dealing with bosons, we should not expect thermodynamic stability in the sense that the energy per particle remains bounded uniformly in the number of particles. Rather, the lower bound of an m-particle Hamiltonian might go towards minus infinity like n squared rather than like n. I now want to rescale my annihilation and creation operators a little bit. Remember, kappa was the strength of the two-body interaction. It's a coupling constant which I will permit myself to vary. So my rescaled annihilation operator in the Heisenberg picture is simply kappa to the 1/2 times the ordinary annihilation operator in the Heisenberg picture. And A star kappa is simply the adjoint of A kappa. That's just a useful definition to save a little space in subsequent formulas. So let phi be a vector in Fock space that describes a system with a finite number of particles, and the m-particle wave functions should be smooth functions of compact support, let's say. Now I define the following state of a system with many, many particles. It's called theta sub kappa, and theta sub kappa is obtained by creating n sub kappa particles out of the state phi. So I have to apply an nth power of the creation operator to my to my reference state phi, and divide by the square root of n kappa factorial in order to keep the norm of theta kappa bounded when n kappa becomes large. Psi naught is simply one of these test functions. Say it's a smooth function of compact support, and just in order to get rid of normalization constants, I normalize the psi naught to have a 2 norm 1. I will choose n kappa to be the integer part of kappa inverse. So you see what will happen. The weaker the interaction between the bosonic particles, the more of these particles I will consider. In fact, the number of bosons that I consider is proportional to the inverse of the coupling constant kappa. Let's now look at the Hartree, the nonlinear Hartree equation. Let psi of x and t be a solution of the nonlinear Hartree equation, which is simply a nonlinear version of the one-particle Schrödinger equation. It is I dt psi equals minus 1/2 Laplace psi plus w psi. This was the external potential acting on the particles. Minus phi c convoluted with psi squared applied to psi. And let's choose as our initial conditions psi of x and time t equal to 0, psi naught of x, where psi naught of x is the function that appears in the creation operator. I also want to look at the
equation, right? It's not clear from this notation, but actually the nonlinear term is a non-local integral.
Absolutely right, yes. So it's an integral differential equation, nonlinear. The mathematicians have a kind of a neurotic preference for the nonlinear Schrödinger equation. So they set phi c equal to a delta function, which, however, for physicists is not a very natural choice. But of course, this phi makes the whole thing somewhat non-local, but that's not the problem.
It's a natural choice if the interaction is the radius of interaction is small.
That's right, but it will not be small. I mean, van der Waals, for example, is a pretty long range, and so we cannot replace it by a delta function. All right, so let's take a solution. It's not difficult to prove global existence and uniqueness theorems for this nonlinear Hartree equation under the conditions on phi c that I stated. Psi of f and t is simply the solution psi of x and t smeared out with a test function f. Now, I want to recall a theorem which was essentially proven by Klaus Hipp many years ago, in about 1974, concerning the classical limit of quantum systems. There was a little problem with the way Klaus presented his result. He must have talked to mathematicians too often. And so he introduced h bars all over the place and let h bar tend to 0. And then, in fact, we had to do some job of translating his results into ones that make sense physically, but the mathematics was more or less carried out by him many years ago. It's the following theorem. Let's take, so here are these rescaled annihilation and creation operators. Let's take a product of n creation and m annihilation operators rescaled by kappa, and let's calculate their expectation values in the state theta kappa. And then let's ask what happens when kappa tends to 0, meaning that the interactions will become weaker and weaker, and the number of bosons will increase like kappa inverse. Well, the answer is that these expectation values converge to a constant, which is a normalization constant depending on the reference state phi, times a product of solutions of the nonlinear Hartree equation smeared out with test functions. So in other words, systems of many, many bosons with very weak two-body interactions have Green's functions that are completely described by solutions of the nonlinear Hartree equation. Or in other words, the dynamics of such a quantum system in the limit of very weak two-body forces is described by classical Hamiltonian dynamics as given by the nonlinear Hartree equation. Pardon?
Is dynamic conversion of Hamiltonian conversion? I mean,
Pardon? What?
it's actually dynamic conversion to small interval, or is just Hamiltonian formula conversion? What is clear?
This is the left-hand side is a function of the times t and the times s.
So time converges to the
Yes, absolutely.
small time.
No. I mean, this is the question of how good this convergence is only depends on how much you know about the existence and uniqueness for nonlinear Hartree, which is under complete control, as Jean will probably tell us. In fact, he probably might not even tell us because it's sort of an obvious result.
What is
So-
the wave function small phi?
Oh, phi was this reference state. All you have to know about phi is that it describes some finite number of particles independent of kappa, and the wave functions should be smooth. It could, for example, be the Fock vacuum. So is it clear what the theorem says? I think it's not the deep theorem mathematically, but I believe it's a very important fact about quantum. I mean, Yossi doesn't look convinced. I'm sorry, Yossi. You have to tell me afterwards what your problem with it is. So what do I want to conclude from this? Apparently the classical limit emerges when I have a lot of particles of the order of kappa inverse with very weak two-body interactions. Of course, there is an issue here, and the issue is how typical these vectors theta kappa are. Now, there are recent results due to Lieb, Seiringer, and Ingvason. Well, you see, it's like in classical mechanics. If, for example, if you show that there is an invariant torus for a Hamiltonian system, but you never find this torus because there are just a few, or there is a very small set in the sense of measures theory of invariant tori, then it is irrelevant because you never see it. So there is an issue here to understand how typical states of the form theta kappa are, for which we know that the classical limit is reached. I think this is in fact an important problem. Pardon? Theta kappa was defined on the previous transparency. Maybe I should recall it if I find the transparency, but it cannot be very far. Well, actually, here. You see, these are states where all the bosons are more or less in the same one particle state, and I just pile them up. Now, of course, these are very special states in the Hilbert space. And so there is an issue about understanding how typical these states are. And there is some understanding of this question for states of very low energy. But I think the understanding is certainly not as good as we would want it to be eventually. Anyway, it gives you some feeling that quantum theory converges to classical mechanics for weak interactions and many particles. So now we have to discuss the nonlinear Hartree equation, because that describes the limiting dynamics of the quantum system. Well, this is a Hamiltonian system. It has an infinite dimensional phase space, which is simply the energy space H1R3. And I choose complex coordinates psi and psi bar. The symplectic 2 form is then I over 2d psi wedge d psi bar. It leads to Poisson brackets of the following kind: psi x and psi y Poisson commute, so do the psi bar x and psi bar y, and the Poisson bracket of psi x with psi bar y is 2i times the delta function. The Hamilton functional of the nonlinear Hartree equation is given by this expression, 1/4 integral over all of space, R3, nabla psi squared plus 2w times psi squared minus phi convoluted with psi squared applied to psi squared integrated. I now return to the notation where this fixed potential phi c is denoted by phi. I drop the subscript c. All right, so it's really a Hamiltonian system. This Hamiltonian system has a certain number of conservation laws. Well, first let's observe that the Hamilton functional is well defined on my phase space gamma. It is bounded below on every sphere Sn in phase space, where Sn is defined to be all those psi's in phase space for which the L2 norm squared is equal to n, where n is some finite number. Let's check that Hamilton's equations of motion are equivalent to the Hartree equation. So psi dot is the Poisson bracket of the Hamilton functional with psi, and I showed you what the Poisson brackets are here. So just by calculation, you find the right-hand side is given by what it is supposed to be if this system is supposed to be equivalent to the Hartree equation. So this works fine. Now let's look at symmetries and conservation laws for this Hamiltonian system, just the way we are used to when we do mechanics. First obvious symmetry is gauge invariance. If you change the phase of the function psi by multiplying by e to the I theta, the Hamilton functional doesn't change. Therefore, n of psi bar psi, which is the L2 norm squared of psi, is a conserved quantity. And of course, you check immediately the Poisson bracket between h and n really vanishes. So that means that these spheres Sn, which we introduced here, are invariant under the Hamiltonian flow generated by the Hamiltonian vector field corresponding to h. When the external potential W vanishes, then the system is Galilei invariant. That means that there are the following conservation laws. The total momentum is conserved, and the total angular momentum is a conserved quantity. And of course, finally, the center of mass motion in this system is inertial. So you just have to figure out what this means for solutions of the Hartree equation, but that's really not hard. In particular, the Galilei group, of course, has the velocity transformations belonging to it. So if you found a solution, psi of x and t, of the nonlinear Hartree equation, then a boosted version of psi of x and t, which is psi of x minus vt, comma t times e to the I times v dot x minus v squared over 2 times t, also solves nonlinear Hartree for an arbitrary velocity v in R3. Now, for later purposes, namely for the purpose of understanding of how nonlinear Hartree manages to reproduce Newtonian mechanics, I now want to look at minimizers of the Hamilton functional for a fixed value restricted to these spheres Sn. So in fact, I'm looking at rotation invariant global minima of the Hamilton functional restricted to such a sphere Sn with external potential W set to 0. Or I should probably hurry up. How many minutes do I have? Oh, I'm really in trouble. So anyway, this is a simple standard variational problem. Here is what we know about this variational problem. You always find these minimizers. They are nice, smooth, exponentially decaying, etc. Then, of course, when you have found such a minimizer, you can boost it, and you you get the moving soliton solution for your nonlinear Hartree equation. It is tempting to imagine that these moving solitons are in fact behave like point particles in Newtonian mechanics. And this is indeed what one can check.
Which particle? Have many particles system, or which particle?
This is,
particle emerges, have many particles, which
look, I realized that this is a slightly complicated story. Maybe it was a bit too much for 45 minutes. We started with quantum mechanical particles, bosons, weakly interacting, many of them. We understood that the Green's functions of such systems approach products of solutions of nonlinear Hartree. So in other words, quantum mechanics reduces to an infinite-dimensional Hamiltonian system in a certain limit. Now we would like to understand how this infinite-dimensional Hamiltonian system reproduces the Newtonian mechanics of point particles. And here it is extremely important that there are attractive two-body forces in the nonlinear Hartree equation. Then these attractive forces will create lumps, and these lumps will behave like point particles. And that's really what's happening. You have to ask the further questions, please, in 3 or 4 minutes. I mean, I'm really in trouble. I'm nowhere near the end. Okay, and let's imagine that. Let's imagine that I started a little late, and so it's okay. All right. So this is the lemma about the variational problem. Since Jean is there, I mean, he will probably explain all these things in much better ways. So I don't have to say much about it. So let's now look again at the nonlinear Hartree. We have seen it's a Hamiltonian system. Let's look at the action. Well, the action is always obtained the same way. You integrate over time the Lagrangian, which is I over 2 psi bar dt psi minus the Hamilton functional. And I wrote out what it is. We will replace the external potential. We will make it very shallow. We will replace W by W epsilon, which is defined to be simply W of epsilon times X. We fix the two-body potential, and we pick K positive numbers, N1 up to Nk, such that every Nj is big enough for a non-trivial minimizer to exist in the sense of lemma 2, which I didn't discuss very much. Let's also imagine that, okay, let delta m denote the diameter of one of these soliton solutions Qn, and let's consider a configuration of k solitons at positions Q1 up to Qk, and such that epsilon is the same as the maximum of the diameter of these solitons divided by the minimal distance between two distinct solitons. Let's imagine this parameter epsilon is much smaller than 1. Well, then you can imagine what happens. We now make an ansatz for a solution of nonlinear Hartree to be a superposition of solitons. Now, since the equation is nonlinear, I have to add an error term, otherwise I don't get the solution. And the error term is H epsilon. Let's imagine this error term tends to 0 as epsilon tends to 0, a little faster than epsilon. The phases that I assigned to the solitons have the form indicated here. And in fact, I'm only looking at finite times, namely times should be bounded by a constant divided by epsilon. Now, by a moderately lengthy calculation, you can verify the following thing. If you plug this ansatz psi epsilon into the action functional that we just saw. Maybe I can show it once more if I find it. It's disappeared. Here is the action functional. I now plug my ansatz into this action functional and compute. What do I find? Well, here is what I find. The action actually becomes the action functional of k point particles, non-relativistic point particles, moving in an external potential and interacting via two-body forces, up to an error term which goes to zero more rapidly than epsilon. So if I view the trajectories of the solitons as parameters to vary, I will have to vary this action functional and check what it gives. Well, it will probably, we hope, it will give me Newton's equations of motion for the trajectories of the solitons up to small error terms. This, of course, depends on smoothness properties of this error, little o of epsilon, which is really what is mathematically the hard part to control in this game. But since I'm a physicist, I don't have to talk about the hard estimates. Anyway, vary now this action functional with respect to the trajectories of the solitons, and you get these nice Newtonian equations of motion with small additional terms that I call aj of t because they describe accelerations. And in fact, these are sort of friction forces. These friction forces are small as compared to epsilon. The average force acting on a soliton is proportional to epsilon. So these are variants of the Newton's equation of motion with a little friction in it. Now, I could go on and tell you what the precise variants of these results are. In fact, we have not done very much yet, but we have considered in great detail at the motion of a single soliton in an external potential to try to see what happens. Well, you find what you expect, namely that the trajectory of this soliton is given, at least for finite times, by a solution of an equation of motion, which is essentially Newton up to a small error term. And you can in fact prove more. You can prove that eventually a point particle moving in a shallow external potential will come to rest because it will constantly radiate a little dispersive radiation that goes out to infinity and that takes away some of its energy. So if you wait for a long time, the particle will simply sit at the bottom of the external potential. Pardon? The radiation is the... Look, I'm looking at nonlinear Hartree. I'm looking at solutions which are of the form a soliton plus a little perturbation. If you look at the equation of motion for the little perturbation of the solitary wave, it satisfies essentially a linear equation. You can linearize around the soliton. Look, the original quantum model reduced in a certain limit to nonlinear Hartree. What does the radiation of the nonlinear Hartree describe back in the quantum theory? It describes a little dust that gets spit off by the system. The system manages to throw out some of these bosons which take off and go towards infinity.
You may have friction without quantum radiation. Classical friction without quantum radiation.
Without what?
Without photons going.
There are no photons. The bosons play the role of the photons.
Why don't we let you finish? Assume that your interaction is attraction, right?
Pardon? very important. If I had had more time, I would have emphasized this a little more strongly. The existence of these essentially point-like solitary wave solutions hinges on the assumption that there is attraction, two-body attraction. If it was repulsion, I would only have dispersive wave solutions and no solitary waves. So in fact, it is very important. Classical mechanics can only come out, point particle mechanics can only come out of quantum theory when you have attractive forces. Fortunately, we have attractive forces, for example, van der Waals attraction.
So you're trying to
Yes. I'm more or less finished. In fact, I can finish anywhere. Really doesn't matter much. Well, then we have a little result on scattering theory. Scattering of waves of one soliton. That is also under control. As you may imagine, that's not so difficult. So let's conclude. I believe we really learned something about the classical limit of quantum theory. At least I have learned something. I may not have been able to transmit it to the audience, but this is not a totally easy story, and it is not so easy to explain it, especially in my present state of body and mind. But it is, I think, a relevant story for understanding quantum mechanics, incidentally also for understanding experiments in quantum mechanics. What are the right questions to ask for the future? Well, we would like to understand more precisely the nature of the friction forces in this mechanical system. We would like to understand what friction really does and how strong it is. This is not very well understood at present. Well, we would like to understand things like how an initial condition converges to a solitary wave plus a little radiation, and the radiation, of course, will become invisible when you go to large times. That's this question number 2. We would like to understand, for example, more about the collapse of binary systems. Imagine that you have the sun in the center and the earth around it, and you describe this mechanical system by nonlinear Hartree, which I showed is possible. Well, then, of course, as long as this parameter epsilon that measured the approach to Newtonian point particle mechanics is positive, there will be a little friction, and in fact the binary system will eventually collapse by friction. This is this is a little similar to what happens in a much harder problem. That's the description of, say, two black holes in general relativity which rotate around each other. There, through gravitational wave radiation, the system will collapse, but it is much more difficult to understand than the systems we are looking at here. Another interesting topic would be to understand structure formation. You look, say, at the big soliton in the middle plus dust around it. This dust is described by an initial condition, psi naught, with more or less uniform density, but with a little perturbation in the uniform density, and you now let it evolve in time. Then, of course, through gravitational attraction, new bumps should emerge, and this should be a good model for structure formation. In fact, I think one could try to do numerical simulations on all these problems and see what they tell us. Unfortunately, these numerical simulations are not totally easy and require big computers. So, in fact, I have no results on numerical experiments to report at this point. I think this is now really the time to stop. Thank you.